So in a synchronous condenser, before going to the synchronous condenser, we should know what will be the effect of the low power factor. The effect of low power factor in a bus bar. For an example, we know that for the power is equal to VA cos phi. Here we consider a single phase supply. For a single phase supply, the power of P equal to VA cos phi. So now we consider the power is equal to 5 kilowatts and the supply voltage of P equal to 230 voltage. Supply voltage of P equal to 230 voltage. We can write down current I is equal to power divided by V into cos phi. First case, we can consider that when a power factor is equal to 0.8, then current I is equal to 5 kilowatt. 5 to 10 to 3 divided by 230 into, for a power factor of 0.8, the power consumed or the current obtained is equal to 27.17 ampere. Second case, when power factor by cos phi is equal to 0.5, where current I is equal to the same power and then voltage, but here what happened, the power factor value is equal to 0.5 and the current is equal to 47.47. Therefore, for a lower power factor, what happened means there will be more power will be obtained from the power supply. There will be more current will be obtained from the power supply. So therefore, if you are making the machine to operate in a lower power factor, then more current will be consumed. So therefore, what happened means this will shows that we should maintain the power factor to be a higher power factor. Okay. So now we are going to see that in a bus bar or by B, in a bus bar we are connecting an alternator, where the alternator will generate the alternator will produce the 3-phase voltage. Okay, it will generate a 3-phase power supply. From the generator, the power will be given to the bus bar. So now what happened means the load here will be connected. The load here connected will be, most of the load will be a inductive load will be connected. In our household appliances also, most of the load will be a inductive load. We know that there will be 3 types of load: resistive load, inductive load and the capacitive load. Resistive load, inductive load and the capacitive load. If you consider resistive load, it will be coming under the unity power factor. Inductive load will be a lagging power factor and the capacitive load will be a leading power factor. So it shows that depending upon the load we are connecting, mostly in our household appliances we will be using resistive load and the inductive load. The power factor will be lagging power factor. The power factor will be obtained will be a lagging power factors. Now what happened means, now just see here. So here in the lagging power factor. So therefore what we are going to mean, we have to improve the power factor. We have to improve the power factor, lower power factor in the bus bar. We have to improve the lower power factor in the bus bar. For that, what we are going to mean, we are going to use a synchronous motor. We are going to use a synchronous motor, where the synchronous motor can be operated in under excitation, and over excitation. You can make the synchronous motor to operate in under excitation and the over excitation. If you are making operating under excitation means it will be a lagging power factor. Under excitation will be lagging power factor and over excitation will be a leading power factor. That is without under no load condition. That is the synchronous motor will be under no load, and if your excitation is the over excitation, then it shows that it will be a leading power factor. Okay. So now here the phasor diagram shows we are taking voltage V phase as the reference. And shows that the current IA leads the voltage by an angle of 90 degree. The current IA leads the voltage by an angle of 90 degree. So now here what happened means the phasor diagram shows for a synchronous motor. Okay. Therefore here V phase is the supply voltage giving it to the motor. V phase is the supply voltage provided to the motor, and EB phase is the back EMF which is induced inside the synchronous motor, and then ER phase is the resultant voltage. So therefore here it shows that this is the phasor diagram for a over excitation, that is the leading power factor. The phasor diagram which is for the leading power factor. Okay. So now what happened means we are going to use the synchronous motor in the bus bar. At that time what will happen? First we are taking voltage V phase as the reference. And most of the load here connected will be a inductive load. So inductive load lags the voltage. The current lags the voltage by an angle of pi. So first what happened? What the meaning of pi 1? The pi 1 indicates that the current I1 is lagging the voltage V phase by an angle of the current I1. Lagging by an angle of the current I1. Now what we are going to do? We are going to connect the synchronous motor to the bus bar for over excitation and no load condition. Over excitation and the no load condition. At the time what will happen means the current here will be a leading current. The power factor will be current. So what happens? The current I2 will lead the voltage. The current I2 will lead the voltage by an angle of pi 2. The current I2 will lead the voltage by an angle of pi 2. Now what happens means if you see the phase addition of I1 and I2, it is called as the effective current. The phase addition of the I1 and I2 will produce a I2T. The phase addition of I1 and I2 will producing an effective current of IT, which shows that the phase angle is reduced by an angle of pi. The phase angle is reduced by an angle of pi. So therefore, by connecting a synchronous motor under no load with over excitation, then it will be act as a synchronous condenser. What is the meaning of synchronous condenser? Condenser is nothing but the capacitor. The condenser is nothing but the capacitor. So therefore, the synchronous motor is acting as a capacitor. We know that capacitor means it is nothing but the leading power factor. That's why the current I2 leads the voltage by an angle of pi 2, and the current I1 here. Where I1 is the current without the synchronous motor. I2 with the synchronous motor. The phase addition of I1 and I2